Hi there, everyone. Thank you very much for joining us today for our webinar on leveraging millimeter wave for 5G. Thank you for your attendance and participation today. If you have any feedback or other webinar topic suggestions, then please let me know by chat, or you can email me later at support@testforcecc.com. Before we get started, I'd just like to let everyone know that this webinar is being recorded and you will be receiving an email afterwards with the recording. So you can go ahead and share it with anyone you think would be interested or rewatch it if you'd like. If you're interested in any of the other webinars we'll be hosting, or to download any of the free resources we have available, such as white papers or application notes, please go ahead and visit testforcecc.com/academy, and you'll find everything you need right there. If during the webinar you have any questions, make sure that you ask them in the Q&A section in the right side of the menu bar, and we will be sure to get to all of those questions at the end of the presentation. And now, without further ado, let's jump right in and talk about leveraging millimeter wave for 5G with Richard Webb, Russell Lindsay, and Joseph Morcerino.
Hello everybody, and thank you for joining us. As you can see from the agenda on screen, we're going to start with a few introductory comments on trends and characteristics of millimeter wave, and then outline some of the problems and challenges of usage. After that, we'll look at solutions and review what it looks like from a deployment perspective. Then we'll hear our sponsors, Anritsu and Fujitsu, talk through their approaches to millimeter wave for fixed wireless access in particular. And lastly, we'll make a few quick concluding remarks before we enter the Q&A section. But without further ado, let's get underway. So I'm going to kick off today's webinar by briefly giving some context around millimeter wave and outline some of its characteristics and challenges, as you can see on screen. So it's a high-capacity line-of-sight wireless connection that can utilize several different spectrum ranges. In mobile backhaul, we've probably seen it most so far, used in the E-band range, around the 71 to 86 gigahertz range, but for 5G fixed wireless access applications, it's mostly going to be utilized lower down in the frequencies, something that we'll look at in a minute or two. It operates with narrow concentrated beam signal for point-to-point connectivity, uses techniques like MIMO and beam forming, but one of its limitations is range, and that's typically in the order of several hundred meters rather than several thousand meters as other microwave frequencies are able to reach. But that still means it's viable for a number of different applications, such as within a local neighborhood where radios, for example, could be pole-mounted to offer 360 coverage, though also in such deployments there's going to be signal attenuation and environmental issues, and that's something we're going to dig into in a lot more detail later on. Other important issues for consideration. Firstly, spectrum, of course. Is it available and for how much? Once you have spectrum, how do you plan the network? How are you going to scale that up in a network-efficient and cost-efficient way? Where do you have permission for siting radio poles, and is there adequate power supply for those? And of course, all the regular backhaul considerations apply for all radio types: capacity, cost, reliability, network operations, and so on. So we're going to be looking at smart transport solutions, which is a vital part of fixed wireless access applications. And lastly, there are, of course, some commercial considerations: the business model, the cost of CPE, building revenue streams, so on. That's a whole other webinar. Today we're covering much more on the network side, but we did want to acknowledge that there are some other elements in the equation as well. So let's compare millimeter wave to what is, if you like, the other flavor of 5G radio, sub-6 gigahertz. How do they shape up? What's the best usage fit? So millimeter wave has channels up to 400 megahertz, whereas sub-6 has up to 100. Millimeter wave is therefore, you could say, compatible for high-capacity services, but only over short distances, as we've mentioned, while sub-6 is more suited to broader coverage scenarios. And as we'll see later, millimeter wave typically suits the small cell deployment model with lower user numbers per cell, whilst sub-6 is more kind of macro cell centric and better suited to those high usage, high user mobility environments. With regards to massive MIMO techniques that can be used in both, but in millimeter wave, that's typically to improve the link budget and also to extend coverage, whilst for sub-6 it can improve spatial efficiency, particularly in a highly loaded cell. There are other differences as well, but I just wanted to highlight some of those differences and show why millimeter wave might be better suited to fixed wireless applications rather than sub-6, in case you were wondering, why don't we just use sub-6 instead, or use it everywhere? So now we're going to look a little bit more about how operators are currently using millimeter wave for 5G, and I'm going to hand over to Russell Lindsay of Anritsu to take us forward and tell us a bit more. Russell, over to you.
Thank you, Richard. Yeah, I think I wanted to do a quick overview of what we're seeing in the world. It's a bit of a moving target. Things change every day, so the minute we put this slide out, it will be out of date. But from what we've seen, I start with Korea. Korea has really focused on trying to be out in front and lead the world in 5G. In last year, they had a government-mandated deadline set for each of their 3 carriers that they would bring commercial networks live in March of 2019, which came to fruition. They even started with enterprise networks at the end of 2018. And now today what we're seeing is that they've already deployed hundreds of thousands of radios across the entire country. They're working on testing those radios, installing them, and improving and mapping their coverage. In Japan, there's also been a big focus on putting out their networks in preparation for the Olympics and the Paralympic Games. We're seeing that they're focusing on really the high denser areas where you see mass transit, like the high-speed rail, or in urban areas like downtown Tokyo. They just finished their spectrum auctions in the sub-6 and millimeter wave. In the U.S., there's really been a high focus on the millimeter wave, both in fixed point wireless and in mobile. We've had a recent auction for the 24 gigahertz spectrums, and we're even seeing now the FCC trying to open up some of those FR1 sub-6 pieces. We're also basically seeing new installations of commercial networks every day, so it seems like every day we hear a new city being announced. Moving over to Europe, and not to generalize too much, but really all major countries are moving their networks forward. We've seen trial networks in the UK, Spain, France, Germany, and many, many other countries. The initial networks in Europe seem to be focused on the sub-6 gigahertz band. There are some testing happening in the millimeter wave, but more focused in the sub-6. But there are new commercial launches being announced every day there as well. China, it seemed like a bit of a slow roll to begin, but now a very fast ramp up. Commercial and trial networks being built in the sub-6 bands. Millimeter wave is under test. The single carriers, each single carrier, which there are a few in China, each are expected to install over 50,000 G-Node Bs around the country in the next several months. And then, of course, around the rest of the world, we're seeing more and more activity as things move along. So that's what we're seeing around the world. Like I said, it's evolving every day, and it's exciting to see it unfold. So back over to you, Richard.
Thanks, Russell. So let's look a little bit more at some of the challenges, particularly on the radio side. And to kick us off, I'm going to ask Joe Mottorino from Fujitsu to talk us through it. Joe, over to you.
Thank you, Richard. The millimeter wave band offers a significant capacity increase for new 5G services. But with this high capacity and high frequencies comes limitations to its coverage area. Millimeter wave has 2 propagation limits associated with its operation. And first is the open air or line of sight coverage limited to around 100 meters. Contrast this to the sub-6 gigahertz radio band that has around 1 kilometer of open air range. The second is its inability to penetrate buildings, trees, other common obstacles in the coverage area. This results in separate strategies and implementation for outdoor and indoor applications. Mitigating these coverage limitations is a densification strategy, where millimeter wave radios have to be deployed around these various obstacles. Instead of traditional cell tower deployment, millimeter wave radios will be deployed on street light, utility poles, and sides of buildings in their serving area, much like we've seen in the past with small cell deployment. As a result, more fiber will be needed to connect these radios, and also, since cell sites are non-traditional, these small cell sites are non-traditional, they'll have limited power and footprint available to them. In the illustration, the outdoor strategy for radio units will be deployed on utility poles in the intersections of dense urban areas to maximize coverage around the buildings. Intermediate deployments will be required to get around trees and other barriers. Let me now hand off to Russell.
Thank you, Joe. Before I get into some of the RF challenges that I want to focus on, I do think it's important to reiterate what Richard was saying about some of the benefits of millimeter wave. Why is it that so many countries and operators and regions are focused on getting this millimeter wave network up? For one, it was extremely important for the world to find ranges of open frequencies to support these dreamed of throughputs that 5G was promising. We've seen in the first couple years of 5G deployment that most, if not all countries, have really had no problem opening up the millimeter wave bands for 5G. On the other side, though, many countries have struggled squeezing out the contiguous bandwidth that's been required for the 5G speeds. You can really look no further than the U.S. for an example of that struggle. The 3 to 6 gigahertz bands have been tied up in other applications, and due to some of the shared spectrum, there wasn't really a desire from the operators to use those. We've seen similar things across the rest of the world. So that's actually recently led the FCC in the U.S. to reassign the 2.5 gigahertz band and have announced auctions for that. It's also important in millimeter wave because with this need for wide bandwidth, it's really rare across the world to see any of the countries auction off more than 100 megahertz of contiguous bandwidth for a single carrier. So like Richard mentioned, according to the 3GPP defined opportunities for 5G, you can have a single carrier up to 400 megahertz. You can also have aggregated carriers, either 4x100 or 8x100 to give you that full bandwidth, especially when we're talking about broadband internet into a neighborhood. And then also, as far as millimeter wave goes, this is really a great time to take advantage of advances in technology. So new technologies in radios and modems, they're enabling things like beamforming and complex modulation schemes that have really taken this opportunity now to the next level. So on that note, now I'm going to focus a little bit more on the RF challenges that Joe's already discussed. As he said in his first slide, it really, on the RF side, it boils down to path loss. You can see here in my slide on the left that the wavelengths of high-frequency signals are naturally much shorter than those of the lower frequency signals. So the wavelengths of a 28 gigahertz signal are 7 times shorter than the FR1 band signals for 5G and 40 times shorter than a 700 megahertz LTE signal. So that really leads us to the two big obstacles, which are free space path loss and object path loss. So on the note of free space path loss, getting the signals from the radio on the tower to a device in the home can be a challenge. So as the wavelengths get shorter, the path loss through oxygen and water can get higher and higher. You have your AM radios that have been transmitting for decades, and they go for miles and miles as they transmit at kilohertz and megahertz. But as signals for mobile communications have gone higher in frequency, we've seen the densification of networks. Millimeter wave represents a new level to that same challenge and is going to require some different solutions. So at 24 gigahertz, you see on this plot that I have on the screen, you see some bumps. At 24 gigahertz, there's a bump where the absorption line and the scattering of water vapor can really attenuate your signals. And then even bigger, as we start to think higher in frequency, when you get to 60 gigahertz, that absorption line for oxygen really bumps up the attenuation of the path loss. So that's going to be an issue as things continue to evolve. Now, fortunately, as far as free space path loss goes, we've actually seen that the performance of these radios has been a little bit better than expected. But the bigger challenge for these signals is going to be the object path loss, especially when we're talking fixed point wireless, where most of the applications are taking a signal from outside and bringing it inside. The shorter wavelengths are quickly absorbed by physical objects like brick, drywall, and even foliage. If you think about sitting in your living room when you go to connect a mobile phone or a PC to a Wi-Fi network, you typically will see all of your neighbors' Wi-Fi networks as you connect to your own. But if those were millimeter wave transmitters, those signals wouldn't even leave the living room. So that's walls, but even windows, which have typically been a conduit for some of these wireless signals to go in and out of a building, are especially problematic because many of them are coated with UV protective films that heavily absorb or reflect the millimeter wave signals. And then furthermore, apart from just getting into the building, there are obstacles around the buildings like metal fences, telephone poles, and trees that are going to attenuate those signals. So all of these technological challenges really lead to some practical challenges. The greater free space path loss means more radios are going to be required, which we talked about densification. This is going to require more planning and especially a lot of alignment with local governments. There have been a lot of fears around the safety of 5G networks, and those fears really come from this public knowledge that these networks are going to have to be more dense. And there's a fear that denser networks means greater RF power, but really it's actually quite the opposite. The reason for the denser network is because of the lower RF power that you're going to see. And so planning that and working with governments to make sure that that is clear is going to be a challenge for the operators. Spectral clearing is also going to be important because these signals and millimeter waves are sensitive to interference. Trying to make sure that there are no interferers in that area is going to be important. And then working through and trying to deal with the increased costs of more networks, installation challenges. They're all going to be practical challenges for those that are making installations. So now I'm going to hand it back over to you, Richard.
Thanks very much, Russell. So we've heard about some of the deployment and densification solutions and we've heard about some of the challenges. But now we're going to hear about a little bit more about some of the solutions, particularly around those areas that Russell and Joe have just outlined. But before we move on to that, I'd like to just remind everybody that you can submit questions to us at any point. If you want to click on the Q&A part of the WebEx interface, you can just submit your question. We'll get to those, or get to as many as we possibly can at the end of the presentation. So now, as I said, we're going to look at some of those solutions. So I'm going to ask Joe to take us forward first. Joe. Oh, big pardon.
Yeah, actually, I think this one's me. So some solutions then to the challenges that I just mentioned. Coverage planning, so making sure that we're optimizing our radios across installations. Optimization means that you have fewer cells, which saves cost and is easier for planning, easier for deployment, is more desirable for governments. Understanding the propagation loss and coverage limits, that's going to be important. So there are RF tools out there that can help in making sure that you view and understand all of the different RF characteristics of signals, and then using those same tools to clear out spectrum. So in advance, going into areas, making sure that you understand the RF characteristics in those neighborhoods, and then pushing them on ahead. And then as far as simplifying the home installation, that's going to be making sure that whatever we do in the home is we've come in, we've optimized our networks, we have radios pointing in the right directions. Then how is it that we make sure that a user who wants to use this service can easily get installation, whether that's through a technician or whether that's within home installation. So now I'm going to pass it over to Joe for more information on that.
Well, thank you, Russell. So we looked at various, let me just move the slide over. We looked at various types of planning from Russell. Let's look at some modeling tools to densify the millimeter wave target areas. So custom modeling and automation tools are used to plan a target area for densification. The outdoor millimeter wave deployment strategy follows that of small cell deployment, as I mentioned before, and is deployed in a mesh. On the right side is a target area to be modeled. Below that, the modeled view shows the density of high-speed internet traffic and proposed cell sites using millimeter wave fixed wireless access technology. There's no standard for these modeling techniques as of yet, but it provides a fairly accurate level of deployment for proposed millimeter wave cell sites. Brownfield deployment for 5G millimeter wave radios will be at 4G small cell sites where mobile network operators already have a presence. Because of the densification strategy for millimeter wave, many greenfield 5G picocell type deployments will exceed the number of 4G small cell sites that you have today. And shown are pictures of non-traditional cell sites for millimeter wave that in most cases blend with the area landscape. Let's look at the transport options for millimeter wave radios in a centralized or cloud-based RAN topology, realizing pooling and cell site aggregation. The transport deployment model is from the radio unit to the distribution unit, as shown at the top of the slide, and referenced as a distribution unit or combination distribution and central unit, shown in the slide as a DU/CU. I've listed 4 transport options based on the deployment limits and considerations previously mentioned for millimeter wave radio. First is dedicated dark fiber. This is the best transport method for fiber-rich environments. Of course, you don't have fiber in every area in terms of service capability, so the next 3 options utilize varying degrees of wave division multiplexing, or WDM technology. Ethernet transport technology is less of an option here due to the power, space, and capacity configurations of millimeter wave radios at these small cell-like sites. WDM extends the capacity of fiber when strands of fiber are limited. Full passive WDM transport is the next in line and offers the lowest cost capacity extension of dedicated dark fiber. However, this lacks any remote visibility for performance monitoring. Next is semi-passive WDM optical transport. This is a low-cost technique, as it is semi-passive. One end is passive, the other end active, and it adds a level of remote visibility through that active side of the network. More about this option in subsequent slides. Now, let me just finish off this slide with the full active WDM. This is the highest cost but most flexible offering in full remote visibility and self-healing topology options. This option is often cost justified in sub-6 gigahertz type radio environments. When dedicated dark fiber, or DDF, is in short supply, semi-passive WDM transport offers the best approach in terms of high availability, performance monitoring, and minimal deployment requirements. In the semi-passive WDM transport option, the RU side, or remote unit at the cell site, is passive, which means it is low cost, it eliminates additional power and minimizes footprint using a WDM with its outside plant enclosure that is slightly bigger than the size of a tall coffee mug or, let's say, a pint-sized beverage of your choice. Smart pluggable optics are installed directly into the radio unit, or RU, to interconnect with the full active hub site. The hub site will have the intelligence to provide remote visibility into the network. Let's look at those networks now. And here are some topology examples of semi-passive use cases showing point to multi-point and linear topologies. At the cell site, the smart pluggable optics automate the operation between sites. And these optics offer service connections for CPRI, eCPRI, and up to 25 gigabit Ethernet type connections. Whether point to multipoint, or linear fiber topology, the passive cell site transport maintains low cost, small form factor WDM, and no additional power needed. Looking at the hub aggregator portion of this semi-passive approach, network elements contain the intelligence options for remote visibility, offering integrated modules for optical digital diagnostic monitoring, or DDM, OTDR, performance monitoring, and latency measurement capability. Let me turn this over to you, Richard.
Richard, are you on mute? All right, looks like we lost Richard here for a second. So let me just kind of pop in here and remind everyone to please continue to answer your questions. We have a lot coming in, and we will get to those at the end of the presented content. Richard, are you back with us?
I'm back with you. Yes, apologies, folks, just got cut off there. Thank you very much to Russell and Joe for giving us a great overview of the deployment and densification solutions and an overview of the transport network options that are available. But now it's really important for us to map those to real-life applications and look at that from a deployment perspective. So I'm going to ask Joe to come back in and kick us off there, and then hand over to Russell to give us some of those real-life examples. But Joe, over to you to start with.
Great. Thank you, Richard. Well, we mentioned before, fixed wireless access is probably the target application for millimeter wave access. And here I'm showing an illustration of fixed wireless access transport for high-speed internet service to residential and small to medium business use cases. The residential and small to medium business buildings will have outdoor antenna arrays that are small, somewhat, about the size of a small-size laptop computer when closed. And these arrays will interconnect to neighboring cell sites that are on utility poles. These utility poles will have passive WDM for transport, as I mentioned previously, as one of the optimal transport methods, transporting multiple sectors of traffic across the network to the distribution or combination distribution central unit devices or network elements in the RAN. The cell sites interconnect to these DUs via the semi-passive transport system. Enhanced mobile broadband is another area that millimeter wave can be used in. A little more challenging here, as you need to highly densify the area. But similarly, this enhanced mobile broadband use case would deploy radio units on utility poles and sides of buildings, interconnected to the DU-CU using a semi-passive approach. So essentially a mobile operations for high-speed internet and mobile communications within 5G. Let me pass this over to Russell.
Thanks, Joe. So I'm going to do something a little more fun. We've had a lot of time out in the field here for the last several years working with some of these networks, and I put together here an example of some of the challenges and opportunities we have in installation of fixed point networks based on several real-world examples that we've seen out in the field. So here we have an example of a new community development where a group of homes have been built and they want to use 5G fixed point wireless for their broadband connection into their homes. But the question then comes to the operator who's coming in to install the network. How do I make sure that I cover this network correctly? So depending on the size of the neighborhood, in some cases we've seen that one single radio actually has enough power to cover an entire development. As I mentioned before, we've seen that in many cases a single radio could transmit several football fields away. So as long as it's installed high enough, it has visibility of the neighborhoods of the homes, one tower with one sector could potentially cover that entire neighborhood. Now, before installation, this operator takes a little bit of time to come out and do some mapping of the coverage. So let's say they install a radio, they've set that radio to transmit, and now they take an instrument, an RF instrument like a spectrum analyzer, they attach an antenna and they walk the neighborhood and they map the power. And they show that, okay, as I walk down this first street, I see plenty of power for me to transmit my signals. Second street, as I get into the cul-de-sac here, now I start to see some dead zones. Same thing as I go into the other street, looks really good for a while, but I'm seeing some dead zones there as well. So as we put that together, now we've seen this operator would see a story and say, okay, there's clearly something that's blocking the transmission of my millimeter wave signals. I'm not going to be able to cover the neighborhood. Why is that? So in this case, they may take a bird's eye look at the neighborhood. And in one case, they might see a tree. So let's say either it's a new tree or a tree that they hadn't noticed was there before. One single tree is blocking coverage to almost a third of this neighborhood. And this is really a key consideration if you think ahead to deployment. If I come into a new neighborhood and I've installed this network, maybe today everything's working fine, but a year from now, 2 years from now, either they've come in and they've installed new fences, new trees. The trees are starting to grow, and the foliage is now taking over in some of the areas. You start to see loss in coverage. So it's going to be very key to working with the planners of these neighborhoods, making sure that there's communication as landscaping is changed, as homes are built on, that those things are taken into consideration for the coverage of the neighborhood so that the broadband network access continues to be there. So in this case, it may be important then for the operator, they have to come in and install another radio. Here's one example. They may be that in order to optimize the network, they can move one over, add another. This can be a bit of a problem as you think through tower availability. If there's not a tower that is in an optimized place to cover this neighborhood, there may need to be installation of something new. That can be expensive. It requires long-term contracts. It's really not ideal. So trying to minimize that can be very important to the operators. Now, interestingly, if we go back to that coverage map, I mentioned before that as they've walked the neighborhood, as they've mapped out the power, it kind of doesn't quite jive where you see a tree blocking this neighborhood and yet you see these green dots which represent good coverage. What is it that's actually happening here? This is an interesting example where you actually can see if you start to do your tests and use a directional antenna to point around and look for the source of those signals, by using a directional antenna and pointing towards the radio, you see that there is no RF power. But interestingly, if you turn that directional antenna down the street towards the home on the corner, you can see here, as shown in this diagram, that there was actually a reflection coming from that home in the corner, bringing that coverage out into the neighborhood. It's very important to understand the direction of that coverage, because let's say you decide as an operator to rely on that reflection then to cover your home, but again, that homeowner chooses to install a tree in front of their home that blocks all of the windows that were reflecting that signal, and now for no fault of your own, you've lost all of that coverage there in that area. So thinking through and optimizing networks in that way are going to be extremely important. So it may be that you decide that a more prudent way of covering the neighborhood is just saying, well, I know that I have coverage for most of this network here. If I have another network, another tower in a neighborhood around the corner, I could install another radio on that tower at a different sector that then could come in and cover those homes that weren't seeing the network before. So those are, it doesn't work simply. It's going to be a challenge, and it's going to be an evolving challenge as the network operators continue to work through how to make this happen for all of their users. So as they do that, it's important to have all of the right tools to make that happen. So now back over to you, Richard.
Great, thanks, Russell. Really nice overview there of the different deployment scenarios. Another reminder, just to keep those questions coming in. We're building up to quite an inbox full of key topics that you want to press us on, so we're going to get onto those towards the end of today's webinar at the top of the hour. But before we do that, let's hear from each of our sponsors regarding their organization's portfolios for this particular environment. So we're going to start with Anritsu and then Fujitsu. So Russell, over to you first of all.
Thank you, Richard. I'm actually excited to have this opportunity to talk a little bit about what we've just announced here in the last several months. So we've released a new spectrum analyzer, and with that spectrum analyzer, we're offering several tools for coverage mapping that I mentioned before. So in this case, we have our Neon MA8100A signal mapping, which is not only outdoor coverage mapping, but indoor 3D coverage mapping. So as you can see in that diagram on the bottom right there, a person can walk a building, measure the RF power of signals coming into that building, and make 3D maps of the coverage. And then this not only works with 5G, but with that same tool, you can make measurements of your LTE networks and your Wi-Fi networks, and all of that information is pushed to a cloud where now you can optimize networks, put everything together, and make sure that your network is being built out in the best way possible. And then I mentioned that going along with that is our new MS2090A real-time spectrum analyzer. So this the advantage of a real-time spectrum analyzer is as you're spectrum clearing, as you're interference hunting, you're able to see intermittent signals. 5G in and of itself is very difficult to find because of the very nature of the signal. They're beamformed signals, so trying to find the maximum power of a signal is going to be a challenge, finding the bore side of that beam in any given area. They're also TDD signals, which means they're time divided, and they're only, when you have power, depending on the amount of traffic on the network, you may only see power somewhere around 5 or 10% of the time. So with a real-time spectrum, with a regular spectrum analyzer, if it doesn't have the right sweep speeds, you may lose some of that power. With a real-time spectrum analyzer, you're always guaranteed to capture that signal. And then even more beneficial is as you see interference from PIM or from repeaters or jammers or anything like that that might be in the network, a real-time spectrum analyzer can help you identify and track those down in a faster, more efficient way. So the performance that we're providing with the MS2090A is designed to be optimized for that use and to give you industry-leading performance. So we're excited about that, and if you have any questions, hope you reach out to us. Now I'm going to hand it over to Joe.
Thank you, Russell. The Fujitsu SmartX Hall solution offers a flexible SDN control and managed transport capabilities for 4G CPRI, 5G eCPRI, and up to 100 gigabit Ethernet transport using a mix of WDM, time-sensitive networking, Ethernet transport, and MPLS segment routing with cloud control plane to dynamically provide network slicing operation for multiple virtual networks within a single high-performance and highly scalable infrastructure. This Fujitsu turnkey services team can also design, integrate, install, and manage the complete end-to-end transport infrastructure for your new network as well as your legacy network. Let me pass it over to Richard.
Great. Thanks very much, folks. So we've pretty much gone through the prepared slide part of our presentation for today. But before we go into the Q&A, I'm just going to spend a few minutes recapping and reiterating some of the points that Russell and Joe have presented for us. So we heard about millimeter wave having some challenging characteristics regarding propagation, range, line of sight, and so forth, and that more cell sites equals more fiber needed. Each site will have limited power and footprint available. There's going to have to be, a plan in there to overcome those limits when planning the network. So that coverage planning is crucial, not just for coverage, but optimizing antenna placement, understanding propagation losses, and so forth. We heard about the importance of simplifying home installation, providing user solutions, processes that minimize time and effort. And this is both a network and a commercial issue, getting customers connected and happy without overspending on lighting them up. But nonetheless, we think it's really, really important to kind of bring that into your thinking when you're planning your network as well. That densification strategy also really, really important for ensuring performance and also the scale up of the network beyond the initial phase of rollout, which might be fairly small scale, but how do you roll that out? How do you kind of, if you like, build a template that you can extend from neighborhood to neighborhood? Using small cells, mesh configuration, modeling techniques, all part of that densification strategy that we heard about earlier. We heard about the importance of the various transport options that Joe gave us a great overview of those and the role of smart transport in deploying fixed wireless access applications. So there we are. So we had a great overview from Anritsu and Fujitsu, I think, of some of the ways in which millimeter wave can be utilized within 5G applications. And now we're going to turn it over to you guys, really, to start picking our brains a little bit, I suppose, with some of the questions that you want us to go into to dig a little deeper. So let's start by having a look at some of the questions that we've had come in. Okay, I'm not going to read out the names of people contributing those questions, but I'm just going to read the questions out for you. So first question, what are the distance limitations of front haul at 25 gigabits? Joe, I'm probably going to turn that over to you first of all, as you've kind of been talking about transport specifically. Joe.
Well, thank you, Richard. So typically, the distance limitations are limited by the radios, the radio unit to distribution unit, and that has been defined and standardized as up to a 100 microsecond latency budget for most applications, most being really all but the ultra-reliable low latency type connectivity use cases. So that's typically that distance of 100 microseconds equates back to about 20 kilometers of dedicated dark fiber. Just the latency loss in the 20 kilometers of dedicated dark fiber will consume that entire latency budget. So you'd have to have very low latency types of equipment on either end to provide that interconnect, such as WDM, which is extremely low latency, or time-sensitive networking, which is also extremely low latency. But in answer to the question, essentially, distance limitation in the front haul is about 20 kilometers.
Okay, thanks very much. I think that answers that question. Russell, any comments, or are you happy to move on?
Nope, that's Joe's area of expertise.
Okay, great. Okay, another one I think that might also be one for Joe to knock out the park. What's the difference between CPRI and eCPRI?
So the difference between CPRI and eCPRI is essentially CPRI used in 4G communications. Both of these, let me back up a little bit, both of these are defined by the CPRI co-op group of RAN vendors that have defined the CPRI protocol and have evolved that into the eCPRI protocol. Essentially, CPRI is used in 4G. It is very similar to a time division multiplexed or type of signal in that it is always fixed, it's always on. eCPRI, on the other hand, has the look and feel more like Ethernet. The difference between the two is that in eCPRI, the low-fi processing is done in the RU, and this converts the CPRI signal into what looks like an Ethernet type signal, which we refer to as an eCPRI type of signal. This is also a variable signal in that when it is off and not in use, it does not use much bandwidth. When it's in use, it peaks, so it operates like Ethernet traffic would operate, whereas with CPRI, it's always on. Whether it's being used or not, it's always on. That full bandwidth is being utilized.
Okay, thanks, Joe. Here's one I think I'm going to turn to Russell to begin with. Russell, you were talking about the different deployment scenarios in local residential neighborhoods as an example, but do you think millimeter wave could be applicable in different vertical scenarios, let's say manufacturing premises? We've had a question in about that. Could it be done there?
I think it absolutely will be done. We've seen in several countries where they are planning actually what they call dedicated 5G networks. So what you'll see in a lot of manufacturing lines is rather than relying on a commercially available network to everybody, you'll see manufacturing buildings work directly with operators to have a dedicated 5G network installed to their plant, so they can manage, if they're trying to manage their equipment, their cloud-based solutions, that stuff will all be given directly to them, and access to that network will be solely on for that company. I mentioned mass transit. It's going to be very popular there, where you have networks that are installed and you have a more predictable environment. It is a little bit easier to plan that network, so you're going to see a little bit of that coming first. And then, of course, the mobile networks as they go along. It's going to take some time to build out. I think I saw another question about when will we see 5G becoming more prevalent or universal. This is a technology that's going to roll out over a decade or more. With this new technology, it's going to take some time for the world to get used to that. And the way the analogy I like to use is I think 5G is it's a Ferrari, and right now we're keeping it in first gear and running it at 5 miles an hour, and it's going to take a while to open it up.
Yeah. Okay. Thanks, Russell. Joe, you're hearing from other vertical sectors around millimeter wave? Are they getting interested? Joe?
So I've been seeing a lot of millimeter wave in terms of fixed wireless access type of applications. So mobile network operators are focusing on that for fixed wireless access type of applications more so, and that's being deployed now. In fact, one of the North American Tier 1 started deployment, actually both started deployment last year, and continue to deploy those today.
Okay, right. Thanks very much. Okay, so the next question, jumping onto a different topic within the subject area. This one's about interference. What technology is used to alleviate interference, particularly when beamforming and MIMO are active? Russell, you were talking about interference. Do you want to handle this one first? And then, Joe, if you want to come in with some comments.
Yeah, so
Russell,
techniques for... Sorry, can you hear me?
Yeah, sure, go ahead.
So techniques for finding interference, it's going to be... obviously, there are several different types of interference. There's going to be a lot of multipath issues here. So utilizing tools that go beyond just throughput. I think there's been a temptation, or really there's a value in using UE devices to do testing, but UE devices are not going to give information on the directionality of signals, some of the higher level signal quality pieces, and then, like I mentioned, interference hunting. So using a tool like a spectrum analyzer, and I mentioned a real-time spectrum analyzer, is going to help you to, with directional antennas, you can pinpoint where these are coming from with fast audio tools that can give you audio reactions to power levels. You can then track them down, triangulate on those signals. We also offer tools like a mobile interference hunter, where you can do drive testing to pinpoint and triangulate interference, go find it, and then identify that source and have it rectified.
Okay, Joe, any comments on alleviating interference?
I think Russell has it covered. Thank you.
Okay. Well, I'd probably hand back to Russell because I've got a follow-up question on the topic of interference. Once interference has been confirmed, what's going to be the best way for regulators to locate, given the short range of coverage of the millimeter waves?
Well, I mean, obviously, the challenges are first, identifying the presence of interference, locating it. I mentioned before the types of things that you might see that might cause interference. There are repeaters that can come into bands. As we start to get into these higher millimeter wave frequencies, things like 24 gigahertz, there may be existing technologies like, pocket radar that's been used for testing the speed of a golf swing or a baseball pitch. Wireless microphones and headsets, things that have typically operated in these higher unused bands, are now may become sources of interference in different areas. And so people who may not have ever even questioned the use of these objects and don't know what sort of problem they could cause. And so monitoring over time is going to be important. So being able to put instruments and tools out that can do spectrum monitoring, tracking that data, and then utilizing that into a cloud-based solution where you can then evaluate and say, okay, here's the timing of certain things. Is it sporadic? Is it often? Actually being able to capture the IQ information of those signals and verify, does this look like, is it a big fat CW signal? Makes it look more like a jammer? Is it something that looks like it's modulated in a specific way? And by utilizing those types of tools, then being able to zero in on what type it is, you can then look for sources, whether it might be something that's in home, maybe something that some device somebody's taking to a park, anything like that. So it's going to be hard at first knowing what all of those will be, but it's going to be more and more prevalent as we move forward.
Okay, thanks very much, Russell. Okay, here's one I think for Joe. This is more related to the transport solutions you were outlining for us. Is the semi-passive active WDM located at the node or at the hub? Joe?
So let me answer that with simply the active WDM component would be at the hub site at the cell site, or I guess what is being referred to as the node, that would be the passive unit. The passive unit would consist of a pluggable optical device, SFP type of device that would directly plug into the radio unit, or in 4G, the remote radio head. This is not an ordinary optical pluggable, but a smart optical pluggable that has processing capabilities and remote communication capabilities, tunability operations to automate the overall operation. And then also at the cell site or node site, you would have the passive WDM itself, the wave division multiplexer. These are small devices. They're in hermetically sealed types of cases, so as to be deployed at these locations for when millimeter wave is used, such as a utility pole or the side of a building type of deployment.
Okay, thanks very much. I've got time just for one more question. It is another question for Joseph, really focused on some of the transport solutions. Joseph, it's specifically around Fujitsu's solution. How does your WDM equipment differ in terms of the millimeter wave scenarios we've been talking about compared to existing 4G type of deployments?
Actually, in 4G, typically what was used outside of dedicated dark fiber was WDM type of deployments for transport. In 5G, you have WDM that can be used based on the use case. For instance, we talked about millimeter wave throughout the webinar and the limitations in terms of millimeter wave that would force it into these locations that are challenged for footprint and power, overall operation. And there you would use a WDM technique, as I mentioned before, a semi-passive type of technique. There are other applications where there might be more space, more power availability, many more channels to be transported from that cell site, whether it's 4G channels from at a 4G small cell site, as well as 5G channels at a millimeter wave site, or even a sub 6 gigahertz site at a traditional tower. This is where there would be many more channels, and therefore it would depend on number of channels, power availability, number of fibers that are available, how you would transport that using either another WDM technique, such as a full active that would provide full remote visibility, or a time-sensitive networking Ethernet transport type of system that would provide precision timing and would open up to network slicing applications for the future.
Okay, thanks very much, Joe. Really appreciate the answers from both Joe and Russell. Unfortunately, that's all the time for the questions we have today. We'll do our best to follow up with everyone whose question we weren't able to answer in the days following the webinar. So we'll try and give you some sort of answer offline. That's all we have time for today. So I'm going to hand back briefly to our moderator.
That was great. Thank you to the three speakers for presenting today and for the very informative webinar. I'd like to say thank you to all of our attendees who made the time to sit in with us for this webinar and for your participation. As I mentioned at the beginning of the webinar, this is being recorded, and we'll send out an email with the recording in the next day or so. And just so everyone knows, we have a new lineup of webinars coming up on our TestForce Academy. So feel free to visit testforcecc.com/academy, and we're always open to hearing your suggestions for new topics as well. So stay tuned and reach out if you'd like to. We had a few questions come into the Q&A section, and we're going to be getting back to those by email since they're a little bit more specific. We'll have the presenter reach out to you on that. I'm going to leave the chat window open for the time being in case anyone else has some questions you'd like to ask. And if any questions do come up later, then don't hesitate to reply back to my email, or you can just send an email to support@testforcecc.com and we'll get back to you with the answers. We've come to the end of the presentation today. I look forward to hearing from you all and hope you have a great day. Thanks again, everyone. Take care.